Hey everyone, ready to roll the dice on this deep dive? We're taking on A First Course in Probability by Sheldon Ross.
Yeah, it's a classic.
And we're going to break it down chapter by chapter. From the basics, like, what even is probability, to some really cool stuff like Bayes' theorem.
Absolutely.
I think by the end of this, you're going to see the world in a whole new way.
You're going to be a probability pro.
Okay, so let's jump right into chapter 1. This is the intro to probability.
Yeah.
Before we get into the nitty-gritty of equations and all that, let's just take a step back. What is probability really all about, and why should we even care?
Well, at its heart, probability is really just a way of measuring uncertainty. It's about, figuring out how likely different events are to happen.
Okay.
And think about it. Every decision you make, every prediction you hear involves some level of uncertainty.
Mm-hmm.
Probability gives us the tools to navigate all that.
So it's not just about, winning at the casino or something.
No, not at all. Probability, it's everywhere. It's in the weather forecast. It's in the stock market.
Wow.
Medical diagnoses. It's even in, the way we understand atoms.
Okay. I'm starting to see how this is way bigger than I initially thought.
Yeah.
So chapter 1 starts off by introducing these, fundamental concepts like sample space and events.
Right.
Can you just break those down for us real quick?
Yeah, so think of a sample space as, all the possible outcomes in a situation.
Okay.
Like if you're flipping a coin, the sample space is heads or tails. Those are the only two things that could happen.
Yeah, makes sense.
An event is just like a specific outcome. So getting heads would be an event
Okay.
within that sample space.
Gotcha.
Now, on top of that, we have the axioms of probability. These are kind of like the rules of the game. They tell us how to assign probabilities to these events. The first axiom is super simple. It says that the probability of any event has to be between 0 and 1.
Okay.
0 means impossible. 1 means certain.
Makes sense. What about the other two axioms? What are those about?
Yeah, so the second axiom says that the probability of the entire sample space, like all the possibilities combined, has to equal 1. Basically, something has to happen right.
Right.
And then the third axiom tells us how to deal with mutually exclusive events. These are events that can't happen at the same time.
So, you can't get heads and tails on the same coin flip
Exactly.
at the same time.
So you can just add up the probabilities of those individual events to find the probability of either one happening.
Okay, so those are the ground rules.
Yeah.
But how do we actually put these concepts into practice? I know that chapter 1 also goes over a few examples.
It does.
What are some of the things that we can use these concepts to figure out?
Well, classic example is rolling a pair of dice.
Okay.
You can use probability to figure out the chances of rolling a 7 or any specific number.
Okay.
It might seem simple, but it's a great way to start visualizing how these probabilities work.
Yeah, and I remember it also talks about drawing marbles from a box,
Yes.
with and without replacement.
Yeah, that's a great example because it shows how probabilities can change depending on whether we put the marble back in or not.
Right.
Think about it like drawing cards from a deck.
Mm?
The odds of getting a certain card change every time you take a card out.
Right. Okay. So we've got these basic examples. They seem simple.
Mm-hmm.
But I'm starting to see how these could apply to way more complicated scenarios.
Yeah, definitely.
So we've laid the groundwork now. Chapter 2 is where things start to get a little bit more interesting, right?
It does. We start diving into combinatorial analysis.
Okay.
This is all about figuring out how many different ways things can happen.
Okay.
So we look at permutations, which are ways of arranging things in a specific order. And combinations, which are about selecting items without worrying about the order.
Okay, so permutations are like arranging letters in a word.
Yeah.
Combinations are like picking toppings through your pizza.
Exactly. And now, Chapter 2 introduces this really cool problem called the birthday problem.
The birthday problem. Okay. I'm intrigued. What is that?
Well, have you ever wondered how many people you need in a room to have a decent chance that two of them share the same birthday?
Yeah, I've heard that it's way lower than you think, right?
It is. A lot of people think you need hundreds of people, but really you only need 23 people to have a 50-50 chance of two people sharing a birthday.
It's like magic.
It's probability. And that's what's so fun about it. It kind of messes with our intuition.
Yeah, for sure.
And reveals these surprising results.
Okay, my mind is officially blown.
Yeah.
So the birthday problem shows us that probability can be super counterintuitive. What other examples does chapter 2 cover?
Well, it goes into things like calculating probabilities in card games, like poker. What are the odds of getting a royal flush?
Oh, wow.
Or a full house? Probability can tell you exactly how likely those hands are.
So if you're good at probability, you can be a card shark.
Maybe. It also tackles the lottery. We all dream of winning big. But, probability can give you a dose of reality when it comes to those odds. Spoiler alert, they're not great.
So chapter 2 is all about counting possibilities, figuring out how likely different combinations are, and maybe even using that to your advantage in a card game or two.
Exact.
Okay, so that's chapter 2. Are we ready to move on to chapter 3?
Let's do it.
Okay, so chapter 3 takes us even deeper. This is all about conditional probability and independence. Can you give us a quick rundown of what conditional probability is all about?
Yeah, imagine you're playing cards and you're trying to guess what card your opponent has.
Okay.
The probability of them having a certain card changes based on what cards you've already seen. That's conditional probability. It's how the likelihood of an event changes based on new information.
So you're kind of updating your beliefs based on what you see.
Exactly. And this leads us to one of the most powerful tools in probability, Bayes' theorem.
Oh yeah, Bayes' theorem. I've heard of that. Not really sure I understand it though.
Well, think about taking a medical test and it comes back positive. Bayes' theorem helps you calculate the actual probability of having the disease, taking into account things like the accuracy of the test and how common the disease is in general.
So it's not just about the test result itself, it's about all the context around it.
Exactly.
Interesting.
Bayes' theorem helps us make better decisions in all sorts of situations where we have incomplete information.
Okay, that makes a lot more sense.
Huh.
So what other examples does chapter 3 dive into?
Well, it looks at the reliability of eyewitness testimony.
Ooh.
That's a big one in legal cases. How accurate are those testimonies? Probability can help us assess that.
Wow. I never thought about using probability for that.
Hmm.
What else?
Oh, and of course the classic Monty Hall problem. It's a game show scenario that always trips people up.
Yeah, I've heard of that one too. That's the one with the doors, right?
Yeah, you have to pick a door and then you get the option to switch.
Right.
It's a great example of how our intuition can totally mislead us when it comes to probability.
Okay, so chapter 3 is all about updating our beliefs, using Bayes' theorem to make smarter decisions, and realizing that our gut feeling isn't always right.
You got it. It's about recognizing that probabilities aren't fixed. They change based on what we know. And speaking of things that change, Chapter 4 introduces us to something called random variables.
Okay,
Yep.
random variables. What are those all about? That sounds kind of complicated.
They're not that bad. Just think of them as labels we give to outcomes in random events.
Okay.
Like if we're flipping a coin, the random variable could be the number of heads we get. It can be 0 or 1.
So instead of just saying heads or tails, we give it a number.
Exactly. Now, random variables come in two flavors. There's discrete and continuous. Discrete variables take on specific values like the number of heads or the roll of a die.
Okay.
Continuous variables can be any value within a certain range, like a person's height or their weight.
So discrete is like counting and continuous is like measuring.
Perfect analogy. And to help us visualize the probabilities for these variables, we have probability mass functions for discrete and probability density functions for continuous.
Okay, so these functions are basically like maps that show us how likely different values are.
Exactly. Chapter 4 also introduces two really important concepts. Expectation, which is also known as the mean. It tells us the average value we expect to see.
Okay.
And variance, which measures how spread out the values are.
So expectation is like the center and variance is like the width.
Exactly. And the best part is Chapter 4 has all these practical examples.
Okay, hit me with an example. What kind of things can we use these concepts for?
Well, let's think about coin flips.
Okay.
We can use probability to analyze how many heads we'd expect to get in like 100 flips.
Right, so we'd expect around 50 heads, but probability tells us exactly how likely that is and how much variation we might see.
Exactly. It goes beyond coins, though. We can model waiting times, like how long will your phone last before it breaks down.
Oh, wow.
We can even figure out the expected winnings or losses in games of chance. That's how casinos make sure they have the edge.
So even though some people win big, the house always wins in the end.
Exactly. Chapter 4 really shows how these concepts apply to the real world.
Wow, my head is spinning with all these new concepts. I need a minute to process.
No problem. We can pick up right where we left off next time.
Yeah, sounds good. To our listener, we've covered a lot of ground today, but hang in there. We'll be back soon to dive into the next part of the book.
Welcome back. Are you ready for more probability?
I'm still trying to wrap my head around random variables from last time.
Well, get ready because Chapter 5 is where we meet some of the most important probability distributions.
Oh boy.
Like the uniform distribution, the normal distribution, the exponential distribution and the gamma distribution.
Okay.
These are like the building blocks for understanding all sorts of random phenomena.
So it's like we're getting a bigger toolbox for analyzing different types of random events.
Exactly. Each distribution has its own special properties and uses.
Okay.
Like the normal distribution, the bell curve.
Yeah.
That one pops up everywhere. Heights, weights, measurement errors, it's all over the place.
So if you were to like plot the heights of everyone in a huge group, it would look like that bell curve.
Exactly. And then you've got the exponential distribution, which is great for modeling things like lifespans or waiting times.
It's like how long until my new laptop crashes?
Exactly. And then there's the gamma distribution, a bit more complex, but super useful for things like wait times in a queue or total rainfall in a period.
Wow, it's amazing how these distributions can like capture so many different things about the world.
It is. And Chapter 5 also revisits a big one, the central limit theorem.
Oh yeah, we touched on that before.
Right. This theorem is super important in statistics. It basically says that if you take a bunch of independent random variables and add them up, their sum will start to look like a normal distribution, even if the individual variables themselves aren't normal.
So even if we're dealing with all sorts of crazy random events, their combined effect will often be this nice bell curve.
Precisely. And that has huge implications for things like election polling, where we're adding up the votes of millions of people.
Right, that makes sense. So we're not just learning about individual distributions, we're learning how they connect and how they emerge from all these different events.
You're catching on. Now, are you ready to tackle jointly distributed random variables in Chapter 6?
Okay, jointly distributed. So now we're dealing with multiple random variables at the same time. How does that even work?
Think about height and weight.
Okay.
They're two separate variables, but they're related, right?
Yeah.
Taller people tend to be heavier.
Yeah.
Jointly distributed random variables, let us describe that relationship mathematically.
So instead of looking at them separately, we're seeing how they change together.
Exactly. We can create a joint probability distribution.
Right.
It's like a map showing the probabilities for different combinations of height and weight.
So we can see how likely it is for someone to be 6 feet tall and weigh 180 pounds.
Precisely. Chapter 6 also talks about independence. Two variables are independent if knowing one doesn't tell you anything about the other.
Like your shoe size and your favorite ice cream flavor.
Exactly. But height and weight, those are definitely not independent.
Right.
And understanding these relationships is key for making predictions and understanding complex systems. Chapter 6 also goes into conditional distributions.
Okay.
These let us see how the distribution of one variable changes if we know the value of the other one.
So if I know someone's height, I can use a conditional distribution to get a better idea of their weight.
Exactly. It's all about refining our understanding based on what we know.
This is getting really interesting. It's like we're building this super sophisticated model of how random events interact.
And that brings us to Chapter 7, which explores some really important properties of expectations.
Expectations like what we expect the average value of a random variable to be.
Exactly. One key property is linearity of expectation. It basically says that the expected value of a sum of random variables is just the sum of their individual expected values.
So if I know the average score for each player on a team, I can use that to calculate the expected total score for the whole team.
Precisely. And we revisit conditional expectation, which lets us update our expectations based on new information.
So if I'm playing a game and I've already won some money, my expected winnings for the rest of the game would change.
Exactly. We also encounter a really cool technique called the probabilistic method.
Okay.
This uses probability to prove that something exists.
Wait, so instead of trying to actually find something, we use probability to show that it has to exist.
You got it. It's a powerful tool in areas like combinatorics and computer science.
Wow, that's mind-blowing. So what kind of things can we use this for?
Well, we can use it to analyze things like the average running time of algorithms. That's really important for designing efficient computer programs.
Wow. It's amazing how these probability concepts can be applied to so many different fields. I'm ready for more. What's up next?
Chapter 8, that's where we explore some of the heavy hitters in probability theory, limit theorems.
Limit theorems. That sounds a bit intimidating.
Think of them as tools that tell us what happens when we repeat an experiment a ton of times. One of the most famous is the law of large numbers.
Okay.
It says that if you keep repeating an experiment, the average of the results will get closer and closer to the expected value.
So like if I flip a coin 1,000,000 times, I should get pretty close to 50% heads.
Exactly. And this is why casinos always win in the long run. They're relying on the law of large numbers to make sure they come out ahead.
So even though some people might win big, the casino is playing the long game.
Precisely. Chapter 8 also takes us deeper into the central limit theorem.
Oh yeah, that's the one that says the sum of a bunch of random variables will often look like a normal distribution.
You got it. And this theorem is the basis for a lot of statistical methods. It helps us make conclusions about entire populations based on just a sample.
So like those polls we see with the plus or minus percentages.
Exactly. Those margins of error are based on the central limit theorem. It helps us understand how much we can trust those poll results.
Wow, so we're connecting these individual random events to these bigger patterns we see in data.
Exactly. Now, Chapter 9 takes a little detour and introduces some additional topics that kind of broaden our probability horizons. We've got the Poisson process, which is all about modeling random events happening over time or space.
Okay, so like if I'm running a call center, the Poisson process could help me model how many calls I'm likely to get in an hour.
Exactly. It's essential for predicting wait times and staffing levels. Then we have Markov chains, which are all about analyzing systems that transition between different states.
So like the weather going from sunny to cloudy to rainy.
Precisely. We can use Markov chains to model those transitions and predict what's likely to happen next. And Chapter 9 even touches on entropy, which is a measure of uncertainty and information content.
So it's like how much information is packed into a message or a system.
Exactly. And it has big implications for things like data compression.
Wow. It's incredible how these abstract probability ideas can be applied to so many different problems.
It really is. Chapter 9 shows how probability is kind of woven into the fabric of everything around us.
Welcome back to our probability marathon. We're on the final stretch now, Chapter 10, and it's all about something that might seem surprisingly tricky: generating random numbers.
Generating random numbers. Why is that such a big deal in probability? It sounds kind of basic.
It might seem basic, but it's super important for all sorts of things. Simulations, computer games, cryptography, they all rely on random numbers. But how do you get a computer, which is basically a deterministic machine, to produce randomness?
Yeah, that's a good point. I never really thought about where those random numbers come from.
Well, Chapter 10 digs into that. It explores different methods like the inverse transform method. It uses the cumulative distribution function to generate random variables that follow specific distributions. Okay, so like if I wanted to simulate rolling a die, I could use this method to generate numbers between 1 and 6 with equal probability.
Exactly. And it goes beyond simple stuff like dice. Chapter 10 also covers the acceptance-rejection method, which is a more general approach that can handle a wider variety of distributions.
So we're not just generating random numbers, we're generating random numbers that have certain properties.
Precisely. That's essential for creating realistic simulations and models. Like if you're simulating the stock market, you need random numbers that behave like actual stock prices.
Right, okay, I'm starting to see how the right kind of randomness is important.
Absolutely. Now, Chapter 11 tackles a pretty common challenge in probability: how to calculate probabilities that are really hard to figure out directly.
I can imagine that as things get more complex, those calculations can get really messy.
You got it. That's where conditional expectations come back into play. Remember those from earlier? Well, Chapter 11 shows how we can use them to make those calculations more elegant and efficient. It's about breaking down a hard problem into smaller, more manageable pieces.
So it's a divide and conquer strategy for probability.
Exactly. Chapter 11 also introduces variance reduction, which is all about improving the accuracy and efficiency of simulations.
So we're not just learning how to compute probabilities, but also how to do it smarter and faster.
You got it. Chapter 11 gives us the tools to tackle those tough probability problems in a really systematic way. Now get ready for Chapter 12, because this one is all about random walks.
Random walks. Okay, what are those?
Imagine someone taking steps randomly forward or backward. A random walk models that kind of movement, and it has applications in all sorts of fields, from physics to finance.
So like a drunkard stumbling around, but we're using math to analyze it.
Well, not exactly a drunkard, but you get the idea. Chapter 12 explores different kinds of random walks, like simple ones where each step is independent of the last one, and more complex ones with dependencies or boundaries.
Boundaries. What happens when a random walk hits a boundary? Does it bounce back or just stop?
That's a great question, and Chapter 12 explores those different scenarios.
Okay.
Like a random walk might be absorbed at a boundary, meaning it stops when it gets there, or it might be reflected and bounce back to keep going.
So it's like setting the rules of the game for our random walker.
Exactly. And those rules have a big impact on what happens to the random walk over time. Chapter 12 delves into some cool properties like recurrence, which means the probability of returning to the starting point, and transience, which means the probability of never coming back.
So some random walks are destined to come back home, and others are wanderers.
You got it. And these properties have real-world applications like understanding how particles move in physics or how stock prices fluctuate.
Wow, it's amazing how this simple model of random movement can connect to so many different things.
And that's the beauty of probability, finding those underlying patterns in randomness. Now, Chapter 13 takes us back in time for a little history lesson.
Oh, a history lesson. Always up for those.
This chapter explores some classic probability problems, like the gambler's ruin problem. It's about figuring out the chances of a gambler losing all their money. And then there's the problem of points, which is about dividing up the stakes in a game that gets interrupted before it's finished.
These problems sound like something straight out of a history book.
They are. Chapter 13 highlights some of the pioneers of probability theory like Pascal and Fermat. It's cool to see how these ideas developed over time.
Okay, so history lesson over. What's next on our probability adventure?
Well, Chapter 14 brings us back to the practical side of things with simulations.
Simulation. I remember we talked about generating random numbers earlier. Is this where we put those skills to use?
Exactly. Simulation is all about using computers to model complex systems or processes. Chapter 14 explores different simulation techniques, including the famous Monte Carlo method. It uses random sampling to estimate probabilities and other stuff.
So instead of trying to solve complicated equations, we can use simulation to run experiments on a computer and see what happens.
Exactly. By running a bunch of simulations, you can get a pretty good idea of the true probabilities. Chapter 14 shows how to use simulation to analyze things like waiting lines at a bank or a call center.
Oh, that's cool. So we can test different ways of managing those lines and see which one leads to the shortest wait times.
You got it. Chapter 14 also explores using simulation for inventory control, helping businesses manage their stock and avoid running out of stuff.
So simulation is a powerful tool for making real-world decisions.
It is, but it's important to make sure your simulations are accurate. Chapter 14 emphasizes the importance of validating your models, making sure they reflect reality. And that brings us to our final destination, Chapter 15, Game Theory.
Game theory. Now, this sounds like fun. It's all about strategic decision-making in competitive situations, right?
You got it. Game theory analyzes situations where what you do depends not just on your own choices, but also on what other people choose. It's used in economics, politics, even evolutionary biology.
So like a game of chess where you have to anticipate your opponent's moves.
Exactly. Chapter 15 introduces different types of games, like zero-sum games, where one player wins and the other loses, and non-zero-sum games where both players can win or lose.
So what kind of strategies do players use in these games? How do they decide what to do?
Chapter 15 introduces this really important concept called Nash equilibrium. It's a situation where no player can improve their outcome by changing their strategy alone, assuming the other players keep doing what they're doing.
So it's like a balance point where everyone is playing their best possible move.
Exactly. Chapter 15 shows how to find Nash equilibria in different games and how they help us understand strategic decision-making.
That's fascinating. And it even covers mixed strategies where players randomly choose different actions to keep their opponents guessing.
You got it. It's a mix of probability and strategy, trying to outsmart your opponent while also factoring in chance. And that's a wrap on our deep dive into a first course in probability. We've covered everything from the basic rules to the complexities of game theory. It's been quite a journey.
It really has.
Yeah.
I feel like I've gained a whole new appreciation for how probability works and how it affects our lives in so many ways.
And remember, this is just the beginning. A first course in probability gives you the foundation, but there's so much more to explore.
So to all our listeners out there, keep exploring, keep asking questions, and keep diving deep into the world of probability. You never know what you might find. Thanks for joining us, and until next time, stay curious.